Hello everyone, I'm Jahidul Islam here to present our paper for IJCNN 221 with my colleagues Mohammad Rukunujaman, Ryan Ahmed, Dr. Mohammad Hassan Kabir, and Dr. Mushe Faraji. Now let's start the presentation. Our paper is titled Efficient Two-Stream Network for Violence Detection Using Separable Convolutional LSTM. At first, let's see what is violence detection. It is a subset of general activity recognition which focuses on recognizing abrasive human behaviors such as fighting, robbery, rioting, etc. It deserves special attention because of its wide applicability in real-time security monitoring systems. Monitoring thousands of CCTV footage manually is redundant and impractical. We need automated systems that should detect violence with minimum time delay, low computational complexity, and yet it should achieve reasonable accuracy. There are quite a few challenges while doing violence detection. Such as there could be varying real-life conditions in the footage captured by surveillance cameras. Some footage might be captured at day while others could be captured at night. And sometimes there could be many ambiguous body movements present in the scene. For example, some people might be involved in violence, whereas others will be just bystanders giving non-violent clues to the system. Now let's look at the related works in the field of violence detection. So earlier works were mostly feature-based methods, which focused on engineering various feature descriptors that could capture the motion present in the video. One such feature was MoSift or motion sift, which was obtained from histogram of optical flows. Then Hessner et al. Proposed violent flows feature, which was estimated by estimating the magnitude of optical flow over time. And other notable features were Blinsky et al.'s improved feature vector for videos to represent both local features and their spatiotemporal positions. But the problem with these feature-based methods is that they do not generalize very well in real-life conditions, and they need a lot of pre-processing and feature engineering. Later on, several end-to-end trainable deep learning-based methods came along and surpassed these classical methods, and they require little to no pre-processing, yet they provide very good performance. Now let's look at some deep learning-based works which are more recent in the field of violence detection. So a category of these deep learning-based works were CNN-LSTM-based networks that were mainly proposed by Sudhakaran et al.'s work of Conv-LSTM and Hansen et al.'s work on biconv-LSTM to solve the problem of violence detection. So they basically employed a CNN-LSTM based network. So here we can see basic CNN-LSTM network in action. The frames are passed into the CNN-LSTM module sequentially one by one, and the CNN part actually generates spatial features, which are then processed by the LSTM to generate spatiotemporal features. They also showed that difference of adjacent frames as inputs boost performance. And however, most of these networks proposed had a lot of memory and computation requirement, which is a problem if we want fast and efficient violence detection methods, which can be deployed in real-life low-end devices. Let's look at a more recent work in the field of violence detection. Recently, Ming et al. Proposed the RW2000 dataset, which is the largest dataset in the field of violence detection, with 2,000 videos captured by surveillance cameras. They also presented flow-gated network, which utilizes 3D CNN blocks with a gated fusion scheme, and they also used optical flows as input. They obtained an accuracy of 87.25%. However, one downside is that optical flow is computationally expensive to calculate. Let's look at the proposed method. And our proposed method is a deep learning pipeline based on two-stream CNN-LSTM network with a fusion layer that combines the feature maps from two streams and some pre-processing steps. The first stream takes in video frames as input, whereas the other stream uses frame difference. As surveillance cameras are mostly non-moving, frame difference highlights the body motions. For the CNN part, we used computationally light and efficient MobileNet version 2. For the LSTM part, we used Separable Convolutional LSTM. Let's look at the preprocessing steps of our system. On the first stream, instead of using frames directly, we opted to use background suppressed frames. We employed a simple technique to estimate the background, which is just averaging all the frames. This average will contain mostly the background because background pixels are present in almost all the frames. And when we subtract this average from all the frames, we get background suppressed frames. On the other stream, we used difference of adjacent frames as inputs. It promotes the model to encode temporal changes between adjacent frames, which boosts the capture of motion information. Let's look at the proposed network of our system. The proposed network consists of two CNN-LSTM architecture with similar configuration, and each stream contains a truncated MobileNet and a separable convolutional LSTM layer. The output from each stream are fused using a fusion layer and passed to the classifier network for classification. Let's look at an integral component of our proposed system, which is separable convolutional LSTM. Unlike regular convolutional LSTM cell, where input gate, forget gate, output gate are computed using convolution operation, in separable convolutional LSTM cell, these convolution operations are replaced with depth-wise separable convolution. This reduces the number of parameters substantially while maintaining similar performance. Here, we can understand how depth-wise separable convolution reduces the number of parameters compared to a regular convolution operation. In a regular convolution operation, the channel-wise and spatial-wise computation are performed in one step using a kernel of size dk into n into n. In depth-wise separable convolution, this process is divided into two steps. These two steps are depth-wise convolution and point-wise convolution. And in the first step, the convolution is performed separately along each channel. Overall, this gives us a reduced kernel size of dk into m plus m into n. And as the kernel size is reduced, this gives us a reduction of computation by a factor of 1 by n plus 1 by dk square. Now let's look into the fusion layer of our proposed network. We experimented with 3 fusion strategies to combine the output feature maps of the two streams. These 3 strategies make 3 variants of our proposed model: M, C, and A. Here M is for multiply, C is for concat, and A is for addition. In the M variant, we element-wise multiply the output of 2 streams, whereas in A variant, we simply add the output of 2 streams element-wise. Let's look at the datasets available for violence detection. The datasets are hockey, movies, RWF 2000. All the mentioned datasets contain equal number of violent and non-violent short clips. Among them, RWF 2000 is the largest, containing 1000 videos containing violence and 1000 non-violent videos. Let's look into the training methodology of our system. We used uniform sampling and extract 32 frames from each video. We used various data augmentation to prevent overfitting. Some augmentation techniques were random brightness, random cropping, Gaussian blurring, etc. CNNs were initialized using ImageNet weights, and separable convolutional LSTMs were initialized with Xavier initialization. And hockey and movies datasets are actually quite small. That is why we first train on RWF 2000 dataset and use those weights to initialize training on hockey and movies dataset. Here we can see the classification results on standard benchmark dataset. We can see that the SEPCON LSTM M variant of the proposed models achieved more than 2% margin in terms of accuracy in RWF 2000 dataset. In hockey fights dataset, the SEPCON LSTM C variant achieved the best performance. The proposed models were able to achieve good performance due to the use of robust and compact modules like SEPCON LSTM, which mitigates the chances of overfitting. Here are the training curves on RWF 2000 dataset. We performed some ablation studies to understand the contribution of various parts of our model. In this ablation study, we are analyzing the contribution of each stream to our model. Using only frame stream, we get 83.75% accuracy, but when we use the frame defined stream, we get 88.25% accuracy. This tells us that body movements and motion patterns produce more discriminative features than appearance-based features like color, texture, etc. In the second ablation study, we try to understand the contribution of Separable LSTM to our model. And we do this by replacing it with 3D convolutional blocks and conv LSTM layers. So when we replace Separable LSTM with some 3D conv layers, we get only 84% accuracy. When we use conv LSTM, we get a slightly lower accuracy, but the number of parameters is increased substantially. But when we use Separable Convolutional LSTM, we get a good accuracy, yet the number of parameters are much lower. This tells us that Separable LSTM is efficient yet robust. Here we show a comparison of efficiency with the models proposed in earlier works. We compared the efficiency of our model using two metrics, parameters and flops. And flops is just the total number of multiplication and addition operation needed for one forward pass. Compared to the previous model, our model uses a lot less number of parameters and calculations. Now let's look at some qualitative results of the proposed model. In the first video, there is little to no movement at all. This is a good indicator of non-violence, so our model predicts correctly. In this video, for instance, the violent action is actually obstructed by a wall. That is why our model predicts incorrectly. In the last video, we can see that the surveillance camera footage contains very poor resolution, and this might cause our model to predict incorrectly. In our work, we propose a new and efficient two-stream CNN-LSTM network. We used Separable Convolutional LSTM and pretrained truncated MobileNet. Our models are lightweight and do not require any computationally expensive preprocessing, which makes them suitable for mobile and embedded vision application as well as low-end system. Our method outperforms the previous benchmark score on the larger and more challenging RW2000 dataset with more than 2% margin. And in our future work, we plan to extract object level features from object detection model because this will inherently focus on the relevant object like people. Another interesting follow-up research could be predicting violence on a per frame basis. This will make the violence detection system real-time and more interpretable. We hope to improve upon our existing works in the future. Here are the references that are mentioned in this presentation. I would like to thank you all for your patience. For more details, please look into our paper.